Dear ladies and gentlemen, I warmly welcome you to the presentation dedicated to composites in the future of construction. Today, I will present to you a revolutionary vision for the development of construction based on composite technologies, which are not only transforming the face of modern architecture, but also shaping the future of sustainable urbanization. This presentation has been prepared by the Łukasiewicz Research Network, Institute of Ceramics and Building Materials, and the Polish Composite Technologies Cluster, organizations at the forefront of material innovation in Poland and Europe. Composites have become the largest application sector for composite materials worldwide, surpassing even the aerospace and automotive industries. This is no coincidence. The architecture, construction, and infrastructure sectors offer unlimited possibilities for utilizing the unique properties of composites. The last 60 years of composite use in construction is a history of continuous innovation in raw material properties, design capabilities, and manufacturing processes. The industry is characterized by versatility and cost-effectiveness, leading to dynamic growth with an estimated annual rate of 5.3%. The global composite market in construction reached a value of $21.8 billion in 2024 and is projected to grow to $36.7 billion by 2030. The 1960s marked a breakthrough in the use of composites in construction. The Les Échanges Pavilion in Switzerland, designed by Heinz Hausdorff in 1964, was a pioneering example of using self-supporting GFRP roof structures with a wide span. Reinforced plastic with fiberglass allowed for a radical reduction in structural weight while maintaining exceptional strength. Simultaneously, the Futuro house in Finland, created by Matti Saronen in 1968, demonstrated the potential of composites in prefabrication. This modular residential home, made of polyester resin reinforced with fiberglass, showcased the possibilities of mass-producing lightweight residential structures. In the 1970s and 1980s, there was significant development in the application of GRC, glass-reinforced concrete, composites in prefabricated facade panels. An example of this trend is the Presidential Palace in Abu Dhabi from 1989, where GRC panels with significantly lower weight compared to traditional concrete panels were used. GRC technology with alkali-resistant fiberglass enabled the creation of lightweight domes for mosques and palaces, revolutionizing the region's sacred architecture. Simultaneously, in France, the Collot house by Pierre Collot was built, demonstrating organic forms inspired by bubble houses, architecture, integrated with the surrounding environment. The period from 2010 to 2012 brought groundbreaking achievements on a global scale. The Guangzhou Opera House in China, designed by Zaha Hadid architects, utilized fiberglass as reinforcement in an alpha gypsum matrix. A form resembling two pebbles was realized using patented high-temperature wax molding technology, where the CNC process allowed for wax recycling. In Amsterdam, the Stedelijk Museum by Bentham Crowell Architects demonstrated advanced capabilities of carbon and aramid fibers in fire-retardant vinyl ester resin. High strength at low weight and fire resistance were achieved through precise vacuum infusion technology. The bridge infrastructure has become another field of the composite revolution. The Forward Harbour Bridge in Rhyl Harbour, North Wales, has showcased an innovative approach to bridge construction with two mirror image spans since 2013. 30-meter platforms lifted by ropes utilized multi-layered fiberglass, E-glass, with a structural foam core and localized reinforcements made of unidirectional carbon fiber. The reduction in weight allowed for shorter lifting times and decreased energy consumption, demonstrating the economic benefits of composites in infrastructure. The Museum of Modern Art in San Francisco, since 2016, has demonstrated the potential of composites in building expansion. A wavy white fiberglass facade with polyester resin eliminated the need for 500 tons of steel support structures. Steve Jobs Theater in Cupertino, a work of Foster Plus Partners from 2017, set new standards in the application of CFRP, carbon fiber reinforced polymer. The roof, composed of 44 carbon fiber panels, each 23 meters long, was assembled in just 2.5 hours. High efficiency with minimal weight and no internal supports demonstrated the capabilities of composites in creating spectacular architectural spaces. The Statue of Liberty Museum in New York from 2019 utilized 134 prefabricated carbon cast panels with C-grid carbon fiber mesh technology. This system provided full structural cooperation and continuous thermal insulation with better energy efficiency than traditional metal connectors. The UAE Pavilion at Expo 2020 in Dubai, designed by Santiago Calatrava, demonstrated the potential of composites in creating dynamic, moving elements. The 65-meter wings made of a hybrid coating of carbon fiber and glass allowed for the unveiling of solar panels in a way that would be impossible with traditional materials. Carbon Haus in Dresden was a breakthrough as the world's first structure made of carbon fiber reinforced concrete. Its resistance to corrosion allowed for a reduction in element thickness, making the structure 4 times lighter than traditional steel-reinforced concrete. This enabled the creation of lightweight, flowing forms that support sustainable construction. Carrostres Wall E+ in France, in the year 2023, presented a construction system made from pultruded composite reinforced with fiberglass. A single-family home demonstrated a new generation of materials offering low weight, high strength, design flexibility, and thermal and environmental efficiency. The Cité Scolaire Internationale Jacques Chirac in Marseille, in 2024, utilized panels made from polyester resin reinforced with fiberglass and Amplitex material, B-Comp, formed using RTM technology. The exterior cladding providing shading for the school building demonstrated durability, weather resistance, and compliance with fire safety requirements while maintaining lightness and a modern appearance. Harker's Island Bridge in North Carolina from the year 2024 represents a new generation of composite infrastructure. Replacing 2 outdated crossings as part of the NC-DOT project, utilized beams made of carbon fiber, reinforced concrete, and deck slab reinforcement with fiberglass. Carbon fiber increased tensile strength and reduced the weight of the structure, while fiberglass in the bridge deck provided durability and corrosion resistance in demanding environmental conditions. The Pulse in Amsterdam from the year 2024 demonstrated the integration of biocomposites with photovoltaics, 1100, i.e., 1100, facade panels measuring 3.6 meters by 2.8 meters with bioresins and PET foam cores, each integrated with a solar panel. On this slide, I would like to highlight the groundbreaking project, the Blue Ocean Dome. The Blue Ocean Dome is the first dome in the world made entirely from CFRP composite, a lightweight yet exceptionally durable material. Its realization required advanced testing and innovative solutions, demonstrating how modern composites are revolutionizing architecture and engineering. The development of these materials in construction began in the 1960s and 1970s with the use of GFRP in lightweight prefabricates. In subsequent decades, GRC, glass fiber reinforced concrete, emerged, revolutionizing facades and molding techniques. In the 21st century, composites, especially CFRP, started being used in load-bearing elements, roofs, bridges, domes, combining different fibers for maximum strength. Today, composites are key to sustainable construction, durable, lightweight, weather-resistant, increasingly integrated with renewable energy sources, and produced from biomaterials. They are the materials of the future, both functional and ecological. The scale of global climate and migration challenges is unprecedented. In 2008, the number of city residents for the first time exceeded the number of people living outside them, and by 2050, it is projected that 68% of the world's population will live in cities. Every year, about 20 million people move to cities in Africa, and by 2030, the population of Dar es Salaam will increase to 11 million, while Lagos and Cairo will each reach 24 million residents. Climate change is driving migration. People are leaving regions affected by droughts, floods, and extreme weather conditions. Urban heat islands cause temperature increases in cities of up to 3 degrees Celsius, higher than in surrounding areas, and cities account for 75% of global greenhouse gas emissions. Migration affects demography, the economy, and culture. The increase in the number of migrants requires understanding their needs and integration. Creating policies that support diversity and inclusion is essential, as this can lead to innovation and economic growth. Challenges include resource management and ensuring social balance. On this slide, I present 4 key challenges shaping the future of construction. In rapidly growing cities, demands on space, infrastructure, and the environment are increasing. Therefore, innovative, sustainable solutions are essential. Social planning. Construction today is more than just building structures. It's about creating spaces that promote integration, quality of life, and genuinely meet residents' needs. Urbanization. More and more people are moving to cities, which requires the rapid and thoughtful development of housing, transportation, and services. This challenge demands smart planning and modern technologies. Climate change. Extreme weather events force a new approach to design. Buildings must be energy efficient, weather resistant, and environmentally friendly. Resource shortage. Depleting natural resources are prompting the industry to adopt low-emission materials, recycling, and circular economy practices. Efficiency and innovation will become key for further development. Materials for the future of construction must meet 4 key criteria: climate adaptation, CO2 reduction, recyclability, and energy efficiency of buildings. Climate adaptation requires adjusting materials to extreme weather conditions, which will become more frequent. CO2 reduction through new technologies and materials is crucial, as construction accounts for 38% of global carbon dioxide emissions. Recycling and reusing materials to reduce construction waste is becoming a priority for the circular economy. Designing buildings that minimize energy consumption through advanced thermal insulation and energy management systems will become standard. Composites play 4 key roles in the construction of the future. First, their lightness and strength enable the reduction of structural weight while maintaining or increasing load-bearing parameters. Composites can be up to 75% lighter than steel while maintaining similar strength. Second, their corrosion resistance ensures the longevity of buildings, eliminating issues related to corrosion of steel reinforcement, which is a main cause of concrete structure degradation. Third, prefabrication and rapid assembly revolutionize the construction process. Composite elements can be manufactured in controlled factory conditions and quickly assembled on site. Fourth, they enhance the energy efficiency of facades and insulation through their excellent thermal and acoustic insulation properties. 4 key innovations are shaping the future of composites in construction. Biocomposites offer eco-friendly alternatives. Materials that combine natural fibers with advanced polymers open new possibilities in designing sustainable structures. 3D printing is revolutionizing construction processes, enabling the creation of complex structures directly on the construction site. Integration with renewable energy sources promotes sustainable development. Composite panels integrated with photovoltaics are becoming the standard in modern investments. Smart structures introduce advanced responsive materials equipped with sensors for self-diagnosis of structural damage and real-time monitoring of the condition of the construction. In traditional construction, concrete, steel, and ceramic brick account for nearly 50% of CO2 emissions over the building's life cycle. The use of sustainable materials, including composites, can significantly reduce the building's carbon footprint by 14% to 45%. The application of composites allows for reducing CO2 emissions in several ways. Reducing mass means lower logistical and transportation requirements and eliminates the need for massive foundations. Increasing stiffness and strength enables a reduction in concrete thickness, and corrosion resistance eliminates the need for maintenance. Good thermal and acoustic insulation translates into lower building operation costs, and structural integrity with sensors enables smart buildings and smart cities. Polish Composite Technology Cluster offers a wide range of composite products for construction. Structural profiles include beams, columns, and panels that enable the creation of lightweight, durable load-bearing structures. Composite reinforcement in the form of rods and meshes replaces traditional steel reinforcement, providing resistance to corrosion and extended lifespan of structures. Facades and cladding made of composites offer excellent aesthetic and functional properties with minimal maintenance requirements. Composite bridges, walkways, and technical platforms provide safe, durable infrastructure solutions. Prefabricated and modular building components allow for rapid project implementation while maintaining high-quality workmanship. The Polish Composite Technology Cluster was established in 2017 and has held the prestigious status of a national key cluster since 2021. The organization unites over 136 members from across Poland, focusing on innovation, ecology, and green energy. The cluster actively collaborates with regional administration and international partners, developing modern composite technologies and promoting Polish companies on the international stage. Total sales revenue of all cluster members in the last 2 fiscal years exceeded 5 billion zloty, employing over 17,000 workers. The organization is open to international cooperation and joint projects in the field of composite materials and technologies. The cluster actively collaborates with the Polish Investment and Trade Agency and the national key clusters in Poland, as well as with composite clusters in Europe and worldwide. The organization co-hosts key industry events in Poland and Europe, such as Composites Expo, LightCon, and the Global Industry JEC Central Europe Forum. Intensive activities within the European Cluster Collaboration Platform, ECCP, and involvement in the Vanguard Initiative, Hydrogen and Offshore, position the cluster as an innovation leader in Europe. The cluster is also an ambassador of the Amulet Liaison Office, a partner of the Optimat Innovation Network, a member of UCIA, European Composites Industry Association, and a partner of the Rescue for EU project and website. The Composite Technologies Cluster organizes virtual meetings on its own platform, trade shows, and conferences, promoting advances in composite technology. The cluster also presents the most important industry news on the websites composite.net, lightweight.pl, pktk.pl, and wodero.info, which provide valuable information about composites and hydrogen technologies. Composites in the future of construction represent a transformative force that is changing the face of modern architecture and infrastructure. From pioneering projects in the 1960s to today's advanced intelligent structures, composite materials consistently demonstrate their potential in creating lighter, more durable, and more sustainable building solutions. The Polish Composite Technology Cluster, as a national key cluster, plays a leading role in this transformation, combining scientific innovation with practical industrial applications. Through collaboration with international partners and intensive technological development, the cluster positions Poland as a leader in the field of composites on the European and global stage. Thank you very much for your attention, and I invite you to collaborate with the Łukasiewicz Research Network, especially with the Institute of Ceramics and Building Materials and the Polish Composite Technology Cluster.